Hello everyone and welcome to the first session of thermodynamics subject, DMM 2673. Today I'm going to introduce you some basic concepts of thermodynamics. We'll learn about the pressure, temperature, units, and also the system, cycle, process, the process path, and so on. So let's go through different slides to see what we are going to teach for today's session. The objective of this session is to identify the unique vocabulary which is associated with the thermodynamics through the precise definition of basic concepts. Today's session is very important because it is the fundamentals of the thermodynamics, and we will need the definition and the basics which we learned from today's session. And also we will review some metric SI and English unit systems. And next I will explain the basic concept of thermodynamics, such as system, state postulate, equilibrium, state or condition, process, and cycle. Moreover, we review some concept of temperature, scale, pressure, absolute, and gauge pressure. This is also important later because we will use these units, these properties actually. Later we will see what is the definition of the property to solve the different problems related to thermodynamics. And also we teach you how use a systematic problem solving technique to solve different problems in thermodynamics area. First of all, let's see what is actually thermodynamics. Thermodynamics is the science of energy. In other words, any place we have energy, we may need to consider that as a thermodynamic system or thermodynamic problem. But before that, we should know what is energy. Maybe the understanding of the energy be a little hard because it is some kind of it seems to be easy, but not actually, because it is very broad and general topic. So, but by definition, we call the ability to cause changes as energy. So anything which has the ability to cause changes, it has energy. And to go in more detail about thermodynamics words, it comes from the two different Greek words as you can see here. Therm, or which means heat, and dynamics, which means power. So thermodynamics is actually the science of heat and power, and sometimes we call thermodynamics as heat and power science. And there is some principle and rules later we will see in more details, but generally one of the most important laws or rules for this science is the conservation of energy principle, which says that during an interaction, energy can change from one form to another, but total amount of energy remains constant. Here you can see an example. As you may know, we have two different types of energy. For a stone on the on an height. So you can see here it has 10 units of potential energy, but because it is not moving, it doesn't have any kinetic energy. So it has 10, you can imagine it has 10 units of potential energy and 0 unit of kinetic energy. and total energy of this stone is, or this system, actually later we will see what is system, is 10 units. When it is falling down, the potential energy is converting to the kinetic energy. So as you can see here in this height, the uh, 7 units of the potential energy is converted to the kinetic energy. But again, you should notice that the total energy is still 10 units. We call this conservation of energy principle, which forms the first law of thermodynamics. It says that an expression of the conservation of energy principle. The first law asserts that energy is thermodynamic property. As you can see here, it deals with energy. And the second law of thermodynamics, which is also important, is it asserts that energy has quality as well as quantity. An actual process occurs in the direction of decreasing quality of energy. In other words, in a system, always energy is going to be decreased. Like until it reaches some equilibrium condition with its surrounding. Later we will see what is surrounding, what is system. But here is an example of conservation of energy principle for human body. As you can see here, this guy received 5 units of energy. 1 unit of energy is stored in the body of his body, and 4 units will goes out as energy out. Still, you can see the conservation of energy. 5 units in, 4 units out, and 1 unit is stored. So the total is equal. And in figure 1.3, you can see the figure to illustrate the second law of thermodynamics. As you can see here, heat flows in the direction of decreasing temperature. And as you know, temperature is thermal energy. So energy is going to reduce. So hot coffee here is 70 degrees Celsius. Surrounding is cooler, only 20 degrees Celsius. So energy from the higher energy place, or here from the place which is higher, will goes through the lower, will transfer actually to the lower point of energy, lower point with lower energy, the point which has lower energy actually. And also we can consider problem related to the thermodynamics with 2 different methods, as classical thermodynamics and statistical thermodynamics. Classical thermodynamics is actually a macroscopic approach to a study of thermodynamics, and it does not require knowledge of behavior of individual particles. So we just consider the problem, thermodynamics problem, from a macroscopic approach. So we do not deal with atoms, molecules, or the particles actually of the substances. And it is useful because it provides a direct and easy way to the solution of engineering problems, and it is used in this text. It may have some error, but it is enough accurate to find the answer for our problem. And the other approach is statistical thermodynamics, which we go to detail of thermodynamics phenomena in a system. Based on this average, the behavior of large group of individual particles is considered, and but we don't use this technique in this textbook or in this subject actually. It is only used to support our finding from the classical thermodynamics. Any place we need to prove something which we get from this classical thermodynamics method or approach, microscopic approach. We will refer to the microscopic approach, but initially we just use the microscopic approach to find the answer for that problem. But where is the application areas of thermodynamics? To be honest, it is, frankly said, we cannot find any equipment, any process which not consist of some kind of thermodynamics. As you can see here in our refrigeration systems, in boats, in aircraft and spacecraft, in power plants, in many other areas, we have some kind of thermodynamics. And this is a house you can see here where, any place which we have energy. Here, solar collector for the house, however, may not very widespread, but if a house has the solar collector, it is related thermodynamics, hot water tank in the house, pump, heat exchanger in that water tank, about the shower as well. All of them are related to the thermodynamics. So it is hard to find equipment or anything which around us which is not related to thermodynamics. So all activities in nature involve some interaction between energy and matters. This interaction actually is thermodynamics. So it is hard to find an area that does not related to the thermodynamics. Here are some other examples. Human body also is the process. Our body also consists or involves some thermodynamics manner. You can understand, because we have energy, we have matter. We earn our energy by consuming different foods as our fuels. Actually, about the cars, it has energy to move its engine. Wind turbine, it's produce energy by rotating its propeller. And air conditioning system, industrial applications, many other area. It is very common and very general area, thermodynamics, and it is very important subject for especially mechanical engineer. Before we go to more detail or to tell you more details about thermodynamics, let's see let's review some basics definition about dimension and units. These definitions are important because later on we will not repeat them, and we will just use them, and it is supposed you already know about them. So first, let's see what is dimension. Any physical quantity can be characterized by dimensions. The magnitude assigned to dimensions are called units. So these two are the units and dimensions. So when we characterize something, actually we should define it as by its dimensions, and these dimensions should have some units. These units can be categorized actually, or are categorized in two different categories, as primary or fundamental dimensions and secondary or derived dimensions, which are based or are made from the primary or fundamental dimensions. The primary dimensions are length, time, temperature, which you may know about them, and the secondary dimension, the most famous one of them are, or we will go to deal with them, are velocity, energy, volume, which are expressed, as I told you, in terms of the primary dimension. You can see here the 7 fundamentals or primary dimension and their unit in SI. Okay, what is SI? We have two different systems. for these units. One of them is metric SI system, which is mainly being used in Europe and some Asian countries. And English system, which is more common in some other countries like USA, they use English system. The metric or SI, the metric SI system is a simple and logical system based on a decimal relationship between the various units. So we will have a unit, then by a logical finding a logical relationship between that one, we can find the value for the other units. Later we will see how we do that. In English system, it has no apparent systematic numerical base, but various units in this system are related to each other rather arbitrarily. I think the most famous one of them is the unit for length. In SI we have centimeter or meter. Actually, the unit SI unit for length is meter, which each meter is 100 centimeters, and you know about that. But in English system is different. The unit of length is foot, and each foot actually is 12 inch. In this course, we are not going to use English system, and we only will use SI system, and we will deal with the problem with SI system. However, you should know about the English system. It is easy. Just refer to your textbook, and you can find the relationship between. However, I will review some of them here, but for more details, you can go to your textbook and find some English system units. Here are the fundamentals or primary dimensions in SI units. For length is the meter, mass kilogram, time second, temperature is Kelvin, electric current is ampere, amount of light is candela, and amount of matter is mole. And you can see here which one of the important units here is Kelvin. This is not Celsius. In SI units, unit of temperature is not Celsius or centigrade. Unit is Kelvin. And also the prefixes. Prefixes are important in SI unit because it is some multiplication of the unit 2 by 10. You can see some of them here: tera, giga, mega, kilo. You may already know about them, but I'm just going to review them. For example, the centi means the unit, the value times 10 power negative 2. Or kilo is the unit times 10 power 3 or 1 with 30 or 1000. The unit multiplied by 1000 will give the kilo. So about the unit, and here you can see some of the units, some SI and English units. As I said, the unit for the mass in SI is kilogram, but in English system is pound. Mass and about the length, you can see here in the SI is meter, in English is foot. You can see the relationship between them. And we have other units or secondary units which are derived from the primary or the fundamental units, like force. The unit for the force is Newton. As you know, force is equal to mass times the acceleration. The unit of the mass is the kilogram. The unit of the acceleration, however, acceleration is also a secondary. Acceleration as a secondary unit as mass divided by second squared. And you can see the relationship between them, how you can convert from one system to the other one. And also you can see unit for the work, which, as you know from physics, work is equal to force times distance. And you can see here, as I said before, the unit for force is Newton, unit for distance is meter. So the unit of work is Newton meter or simply joule. So 1 Newton meter is 1 joule as the unit of the work. We have other units for the work like calorie, like BTU, and you can see the relationship between the joule and these the other units as well. We may deal with some of the example for this unit. You should know how to convert each one of these units to each other. And here you can see an example how is the relative magnitude of the force units or Newton, kilogram force, mass, and also pound force. Here is an example how is the relative magnitude of these 3 units, which all of them are for the mass. And about the weight, weight actually is the multiplication of the mass of any object or body actually times gravitational acceleration, like what you see here. W is equal to mg. Unit of W is Newton. So W or weight is some kind of force actually, but m is the mass. So mass of the body is constant, but the weight can be different when the gravitational acceleration is different. So the weight on the Earth will be different from the weight of the body on the moon because of the difference in the gravitational acceleration. On the Earth's surface, roughly the gravitational acceleration is 9.8 meter per second square. And here you can see also the the different method to show the weight. As I said, you can see here the gravitational acceleration at sea level on Earth is 9.8 something, which the weight for 1 kilogram mass of any substances is this much, which is equal to 1 kilogram force. So 1 kilogram force is this much of Newton. And about pound force, also when because the gravitational acceleration is 32.17 something foot per second square, you can see the weight will be this much, which is equal to 1 pound force. And about the energy, as I said, its units can be joule or kilojoule or BTU. You can see here how much will be the energy from the burning of a match. You can see here it will be about 1 BTU or 1 kilojoule of energy. And also we have specific weight or gamma, which is the weight of a unit volume of a substance. So gamma is equal to rho times g. G is gravitational acceleration and rho is density of the material. Density is actually, you may know about that, it is the ratio of the mass by volume of the substance. The important notice about using these dimensions is dimensional homogeneity. In other words, you should be careful to use the same dimension in all of your equation and calculation. So when you are using Newton, for example, for the force, you should always in that equations or in that problem use Newton. You cannot change from Newton to pound to directly, you should do some conversion. So as you know, all non-primary units, which we call that secondary unit, can be formed by combination of primary units, as you can see here. They can, but the other method which we can use is express them conveniently actually by unity conversion ratio. What is unity conversion ratio? As you can see here, 1 Newton of force is 1 kilogram times meter per square second squared. So the result of this division actually will be 1, or unity conversion, or 1 unit. Also for the force in English unit, still the convergent ratio is unity. We can use this definition, this unity conversion ratio, in our equation to find the answer in terms of each one of the units which we have. So dimensionally homogeneous is very important to solve the equation and problem. So unity conversion ratio are identical, equal to 1, and are unitless. This is unitless because this, the amount of this is equal to this one. So this one is unitless. So this can be, we can put this unity conversion ratio for many of the units in our equations to find the final answer according to the desired unit. You can see here some of these examples of unity conversion about the kilojoule. You can see 1 kilopascal is 1000 Newton meter square. The result of this is 1. It is unity conversion ratio actually. And so on. 1 minute is 60 seconds. So the result of this is 1. This we call them, as you said here, unity conversion ratio. So every unity conversion ratio, as well as its inverse, is exactly equal to 1. And here is some example of that. And this is very important. Every term in an equation must have the same unit. Do not forget to follow this instruction to solve different problems. As you can see here, the weight of 1 kg mass is 10 Newton actually. And you should also avoid to confuse between the mass and weight. The unit of the weight is Newton, and the unit of the mass is kilogram. So do not confuse between them. 1 kg will be 9.8 something Newton on Earth. So please do not confuse between mass and weight. They are two different things, but usually we may in our conversation we use the word of the kilogram words to describe the weight of the material. It's okay in our conversation to use that, but until we solve a problem, we should use the the scientific words for that. So for the weight we only use Newton. For the mass we will use kilogram or its derivation like gram and so on. Okay, let's continue our session with the systems and control volume, which is more specific for thermodynamics. System is a quantity of matter or a region in space chosen for a study. As I said, about the examples I told you about our body, about the cars, about the turbines, how we are going to discover the matter relationship between the matter and energy in this this equipment. First, we should choose the system which we are going to study. So we should quantify a certain amount of the matter or a region in space for our study. We call that a system. For example, in an engine, we can choose just the cylinder, one cylinder, or the space inside the cylinder as our system. Then we are going to study this system. How much is its energy? How much is its mass, pressure, volume? Later we will see what are the important properties for a system in the thermodynamic science. And what is surrounding? Anything outside of this system, we call that surrounding. So the mass or region outside the system is called surrounding. And the border between the system and surroundings is called the boundary, which can be real or imaginary surface. Like you can see here, for example, here is a two example. Here, is a system which we, it can be some region in space. It's okay. It can be our system, but you can see here, the border is imaginary, but sometimes it can be the space inside in a side of the a cylinder and a piston, and you can see here we have a real border for our system. The mass inside this is our system actually. And the boundary, you can see here, real boundary, here is imaginary boundary. In other words, we have something here as a border, but we don't have anything here. It is just our imagination about this border. And these boundaries can be fixed or movable. Here in this system inside the cylinder, you can see here these valves actually are the borders of the system, and you can see, because this is a piston, can move upward and downward. So the border, this border is moving boundary, but the other border are always fixed. So we call them fixed boundary. So the boundary can be fixed or moving. And the other important things about the system is which it is a closed or open system. Here is an example of the closed system. As you can see here, we don't have any mass transfer between the system and surrounding. So there isn't any mass transfer through the border of the system. So mass transfer, no, but we have energy transfer between the system and surrounding, or from the border of the system actually. So this is closed system. But sometimes we have something like this. This is, compare these two. This is a cylinder, this is piston, movable, and this is same equipment, but we add something like this, and a valve to the cylinder. Then mass can pass through the border to the system or from the system. So here, as previous system, we have fixed boundary, moving boundary, but here we have mass transfer between the surrounding and system. We call this open system, which in this case we call the system as control volume. So when the system we choose to study in thermodynamics aspect, if we have some mass transfer from the border of that system with surroundings, we call that control volume actually. So control volume is a properly selected region in a space. It usually includes a device that involves mass flow such as compressor, turbine, and nozzle. So usually when we have a compressor or turbine or nozzle, we need to choose a region in a space, which we call that control volume, to study. And both mass and energy can cross the boundary of a control volume. This is the difference between open and closed system. In open system, we have mass transfer. In closed system, we don't have mass transfer between the system and surrounding. And control surface is the boundaries of a control volume. So according to the definition for control volume, we can define control surface. Control surface is the boundary of control volume. Here is control volume. This is the boundary, so we call them control surface. As you know, when we have volume, the border will be surface. And these boundaries can be, or this control surface can be real or imaginary, as you can see here. These borders are real. This is a turbine or a nozzle actually, as we choose our control volume like this. These borders are real boundary, and these two are imaginary boundary for this control volume or open system. And you can see here another example of open system or control volume. Here is a water heater, and you can see we have mass transfer by these tubes to the system and going out from the system. Cold water comes to the system, hot water goes out the system. So this is an open system because of the mass transfer between the control volume or the system and surrounding. And this was definition or for the open and closed systems and boundaries. Now we know what is the properties, what is the system. Let's see what are the properties of the system and what is important about the system. Properties, any characteristic of a system, we call that as a property of the system. These properties are, some of them are familiar for us, like pressure, temperature, volume, and mass. But we divide these properties to different categories as intensive and extensive properties. Intensive properties are those properties which are independent of the mass of the system. So no matter of how much is the mass of the system or the mass is changed, the temperature and the pressure and density of the system will be constant. So we call these properties as intensive properties because are independent from the mass of the system. And on the other hand, we have extensive properties, which are properties which are dependent to the mass of the systems, or they are dependent on the size of the system. Like mass, as you can see here, like mass and volume. So mass and volume are extensive properties of the system, and as intensive properties of the system, we have temperature, pressure, and density of the system. And we have also some specific properties of the system, which is based on the extensive properties. So extensive properties per unit mass are called specific properties, like a specific volume, which is a result of the ratio of the volume and mass, or a specific energy of the system, which is the energy of the system divided by the mass of the system. And the other important things about the system is continuum. As you may know, matter are made from the atoms. But about the solid material, you know, they are packed and close to each other. But for the gas states material, the material which gas state, it is the atoms are not close to each other, and they are distributed in a space, in a region. So it is convenient, actually very convenient, to disregard the atomic nature of a substance, and we use it as a continuous, homogeneous matter which with no holes. So we call that a continuum. This idealization, or actually the continuum idealization, allows us to treat properties as point functions and to assume the properties vary continually in space with no jump discontinuities. In other words, however, in the real world, we may have some changes for gas inside a balloon, for example, in different point of that space. But we can imagine that it is continuous space, and the molecules and the properties are distributed evenly in that system, and the result of our consideration or calculation will be close to the time when we do not imagine a system as an ideal homogeneous system. However, if we do not use this idealization or assumption, it may be very hard to calculate the properties, to find the properties of a system. And this idealization is valid as long as the size of the system which we deal with is large relative to the space between the molecules. This is important. So we can use this idealization when the volume of the system is much higher than the space between the the particles or the component of the system. For example, the molecules, as you can see here is an example. We have gap between the molecules, the void, space between the molecules. But when the size of the system is much higher than the size between the molecules, we can consider the system as a continuous system. And this idealization usually can be used for most of the problems, practical problems, because the volume which we choose for as our system is usually much higher than or bigger than the size and the space between the molecules or atoms in the system. So in this text, we will limit our consideration to substances that can be modeled as a continuum. So always we can use this idealization in our problems in this course. Two other more important properties of the system are density and specific gravity. As you may know, density is the ratio of the mass and volume of the substance, and a specific volume, or let me first introduce specific gravity. Specific gravity is the ratio of the density of substance rho to the density of some standard substances at a specified temperature. Usually, the specific gravity of the substances is defined according to the density of the water at 4 degrees Celsius. So density of the substance which we are going to find the specific gravity for that, divided by the density of the water at 4 degrees Celsius, will give us the specific gravity of that substance. This specific gravity is important because then we can compare, different materials in terms of the gravity, or we can eliminate the density from our calculation, and we can just use the specific gravity of different materials in our calculation. Later we will see how we can use this specific gravity. And a specific weight is the weight of a unit volume of a substance. We show that by gamma sub s is equal to density times gravitational acceleration on Earth, or at sea level actually. So the weight of a unit volume of a substance is a specific weight. And here you can see an example to calculate density of a substance and also the specific volume. Specific volume is, inverse of the density. Volume divided by the mass, or 1 by rho as a density. So by knowing the density, we can calculate a specific volume. And in this table 1.3, you can see specific gravities of some substances at 0 degrees Celsius. You can see for water, for sure, it is 1 specific gravity because density of water divided by density of water. So it will be 1. You can see for some other substances here, specific gravity for blood, seawater, gasoline, ethyl alcohol, mercury, wood, gold. You can see how is the specific gravity. As you can see here, some of them are the specific gravity of some of them is higher than the water, and for some other is less than water. And you can see for air it's much lower than the for gas material. For example, here as air is much lower than the specific gravity of the water. And as you can see here, the pressure is also mentioned here. Why pressure is mentioned later we will see, because pressure is for the gas state, for the material in gas state, the pressure is effective on the volume of the material. So when volume is changed, density will change as well. So to find the specific gravity of the gases, we should mention its pressure. The pressure which we have measured in it, we have measured in each we have measured the volume of the material. Okay, now let's see what is a state, what is equilibrium condition or state of a system. Actually, thermodynamics deals with equilibrium states. As you may know, equilibrium in words means, some kind of stability, no change. So you can see here the definition of that. Equilibrium is a state of balance. For example, you are going to study, the mass relationship between the mass, temperature, and volume for this system, which is inside the cylinder and piston. This is, in this state, in just one moment, we can measure this. The mass, temperature, volume, everything can be measured. But imagine it is changing. When this piston start to going upward, it will change. The volume will change. When volume change, temperature will also change. Our mass will be constant. So this state is defined as one equilibrium condition, state 1. Then from this state to reach this state, then this piston start to going upward to reach this place. This is a state 1, this is a state 2. In both of these two states, no mass is constant, but temperature and volume is changed. But in this specific point, it is constant. This place is constant. Between these two, it is in transient. It is changing, and we cannot actually, calculate or deal with that kind of system. So usually in our calculation, in our consideration, we should know about the equilibrium state. Sometimes one of our assumptions is to see the problem in an equilibrium state. In an equilibrium state, there are no unbalanced potential or driving force within the system, like this, like this. Nothing is changing. So we call that equilibrium, state of balance actually. This equilibrium can be in terms of different properties. If the temperature is constant, we call that thermal equilibrium. If the temperature is the same throughout the entire system, we call that thermal equilibrium. If there is no change in the pressure at any point of the system with time, we call that mechanical equilibrium. If a system involves two phases, and when the mass of each phase reaches an equilibrium level and stays there, we call that phase equilibrium. In other words, we don't have any phase changes in the system. And a chemical equilibrium, I think you can guess about that, when we don't have any chemical reaction in the system. The chemical composition of a system does not change with time. That is, no chemical reaction occurs in the system. We call that the system is in chemical equilibrium. You can see here for an example of a closed system before and after sometimes you can see closed system reaching thermal equilibrium. Here here the system is not in thermal equilibrium. You can see 20, 23, 30 degrees Celsius. It is changing after a while. Hold the system, all of the point in the system will be in 32 degrees Celsius. The temperature is same throughout all of the system. And if we leave the system like this, and if we don't have any mass, any energy transfer between the system and outside, or if we have it reached, the outside is also 32 degrees Celsius, so the system is in thermal equilibrium. This is important later because we can just deal with the system when they are in equilibrium condition. For example, we can talk about temperature of the system when it is in thermal equilibrium. If it is not, how we can deal with this system? The temperature at each point of that is different. When temperature is different, other properties also may be different. And however, sometimes we can use the state postulate. The number of properties required to fix the state of a system is given by the state postulate. The state of a simple compressible system is completely specified by two independent intensive properties, like what we have in this system. Temperature is constant, volume is also constant. So the state of nitrogen is fixed by two independent intensive properties. So we have a state postulate for nitrogen for the system which we have here. And a simple compressible system is actually if a system involves no electrical, magnetic, gravitational, motion, and surface tension effects. We call that simple compressible system, like what we have in this cylinder. This is simple compressible system because we don't have this electrical, magnetic, and so on, and it is also compressible. So for a simple compressible system, which we can specified by two intensive or independent properties, we have a state postulate. So these two, only two properties can give us the state postulate. This will give us the system which we can use for our calculations for the thermodynamics properties of the system. Okay, now let's see what is a process and what is cycle for a system. As I showed you in a previous slide, we have different states for a system. For example, here, this is system, state 1, state 2. What is changed during this process? The mass is constant, doesn't change, temperature has not changed. What is changed? The volume. State 1, state 2, system is same, but the volume is changed. Two different uh, uh, equilibrium states. We, going from this state to a state 1 to a state 2, we call that a process. During a process, it will go to a state 2. The system from state 1 goes to a state 2. We call that a process. So any change that the system undergoes from one equilibrium state to another is called process. Like what we have here. Imagine this is the system inside, this is the cylinder. This is a cylinder. The volume is changed. The property, actually it can be property A, property B, can be temperature, volume, or pressure, volume, and so on. From state 1 to state 2, it is changed. During this process, here is one equilibrium state, here is another equilibrium state. We call this a process. During this process, from state 1 goes to state 2. But how the system goes from state 1 to state 2 is process path, or the series of states through which a system passes during a process. This is a process. If you notice, the process is made by different states. State 1, actually we have equilibrium state 1 here, 2 here. We are not interested about them. We have a transient state here, but any of them has, here it's properties B1, properties B2, properties B3. Let me show like this. It is like this. Any point has, B1, actually B1 star, B1 like this, and a like this. We have some state also between. Going from this state to state 2, the process happened and will go through all of these states. So the series of states through which a system passes during the process is the path of that process. To describe a process completely, one should specify the initial and final state and also the path it follows. So to know what is the process, we should know initial and final state and also the path. And also we should know interaction with the surrounding. During that process, how will be the interaction of the system with the surrounding. According to this interaction with the surrounding, or the path of the process, we have quasi-static or quasi-equilibrium process. When a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times. In other words, we imagine this cylinder and piston, and we are going to use force to push this piston. We have two options: push it very fast compression, so the pressure of the system, the properties of the system will be changing during this process, actually, because we are using very fast compression. But if we just slowly compress this or push this piston, in whole process, the state or the properties of the system will be close to an equilibrium state. So we call that quasi-equilibrium state. So if the process happens very fast, it is non-quasi-equilibrium. If it is happening very slow, this fast and slow is in terms of the changes in the system. If the changes in the system is not too much during the process and it is close to a equilibrium state, we call that quasi-equilibrium. Just you should know that. And the process diagram plotted by employing thermodynamic properties as coordinate are very useful in visualizing the process. Later on, we will see, for different thermodynamics problem, you need to draw different graphs because it helps you to understand how the changes is happening. Usually we are interested to know how much will be the final pressure of the system. For example, imagine a cylinder and piston here. For example, we have imagine this is we have some kind of combustion here. Energy is released. Then it changed. The volume is changed. When volume is changed, pressure is changed. We can draw this, then because the initial volume and final volume is easy to measure, and initial pressure also we know about that. Then we are interested to know how much will be the final pressure. We can easily by drawing this graph find that. But we should know about the process. How is the process? How is the process? And some common properties that are used as coordinate are temperature, pressure, and volume, or specific volume. Later we will see how to draw these graphs. PV diagram is very important diagram in thermodynamics. You should know how to draw it for different processes. Also the prefix iso, you will see this prefix for many of the process. Here is the process. The process path, it depends on the which type is the process. So we use iso in the before the process name when a process for which a particular property remains constant. For example, isothermal process is a process which during that the temperature or T remains constant. Isobaric process means the process which during that the pressure is constant, remain constant. Isochoric or isometric process is a process which during that a specific volume remain constant. So this is three different type of process in thermodynamics: isothermal, isobaric, and isochoric. Which in isothermal, in which one of them, one of the properties of the system is constant. And the other important definition is cycle, a process during which the initial and final state are identical or same. In other words, the process here we have this process, and process path is this one from initial state 1 to state 2. If it again come back to a state 1, another process, we call that a cycle. So the cycle can be a combination of different process. We can have two process, then we can call that a cycle from state 1 coming back to a state from 1 to 2, from 2 coming back to state 1, then it's made a cycle. And the other type of the process is steady flow process. Imagine a system, a closed system. Actually, it is a control volume here. We have mass in and mass out of the system. So it is an open system. But this mass in and mass out of the system, doesn't change as you can see here, doesn't change the properties of the system by time. So we call that a steady flow process. We have a flow of mass to the system. By its properties, you can check temperature is constant, is time 1 p.m. again same system at 3 p.m. After 2 hours, however, we have a mass in to the system. The temperature has not changed. 300, 300, 200, 200, and the system is not changed because of this mass. So we call this a steady flow process. The term steady implies no change with time. Later on, from now on, anytime we say something is a steady, it means, for example, a steady system means nothing changed about that system with time. Our pressure is steady in the system, it means it is not changing with time. Or when we say ratio is steady, it means the ratio is not changed with time. I mean, steady means no change with time. And the opposite of steady is unsteady or transient. Here we have steady flow to the system. So the mass flow rate is constant with time. So it is steady, no change with time. And it is not effective on the system. So we have a steady flow process. A large number of engineering devices operate for long periods of time under the same condition, and they are classified as steady flow devices. About the turbines, I don't know if you know about it. What is turbine? Turbine is a device which the flow comes to the propeller and produce energy, produce movement or work for us. But the flow rate is constant. We call that a steady flow device. Why this is important? Because again, we can choose a control volume for that. If this mass to and mass out of the system, this flow to the system is changing the properties of the system, how we can calculate the properties of the system? Temperature is changing always. In each second, temperature is changing. So how we can calculate its efficiency? How we can calculate the work of the system? How we can calculate the energy of the system? It's changing in each time. So we can idealize the system and study that as a steady state system. So a steady flow process is a process during which a fluid flows through a controlled volume steadily, like what we have here. And a steady flow condition can be closely approximated by devices that are intended for continuous operation. Here's some examples for the devices which we have a steady flow in them, like turbines, pumps, boilers, condensers, and heat exchanger, or even power plants or refrigeration system. All of these you will later see which they include some kind of flow, and this flow in many cases can be studied as a steady flow process. The other important property of a system is temperature, which by Zero's law of thermodynamics we can define that. Why we introduce Zero's law of thermodynamics after why we have Zero's law of thermodynamics actually? We could just start from first law, then second law, third law, something, and so on. But why we have Zero's law? Because this law is discovered after first and second laws. Then we need to go back and define and this law is the priority of that is before first law and second law. According to this law, or Zero's law of thermodynamics, if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. Okay, let's see what is thermal equilibrium first. Imagine we have this system and it is isolated. We have iron with the temperature of 150 degrees Celsius. We have copper with temperature of 20 degrees Celsius in that system. If we leave system for a while, the final temperature of the whole system will be 60 degrees Celsius. This is the equilibrium temperature of the system. And we have this because of the heat transfer between, or energy, heat transfer means thermal energy transfer between these two material, and this is the zeroth law of thermodynamics. By replacing the third body with a thermometer, the zeroth law can be related as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. You can see here two bodies reaching thermal equilibrium after being brought in contact in an isolated enclosure. So anytime we have two different substances with different temperature in contact with each other, they try to reach an equilibrium temperature like what we have here. Temperature of copper is increased. Temperature here for iron is higher than copper. For iron is decreased. For copper is increased. Some thermal energy from iron is transferred to the copper. So finally, they reach a same temperature, 60 degrees Celsius. And how we measure temperature? All temperature scales are based on some easily reproducible states, such as the freezing and boiling point of water. In other words, we don't know, why we say temperature for today, for example, is 20 degrees Celsius. Where is the source for the Celsius? How we can define that? Why it is not, the temperature, how is defined is according to the some specific points. We call the ice point of the water as the 0 degrees Celsius, and steam point when the water starts boiling as a 100 degrees Celsius, for example. Then from from 0 to 100 degrees Celsius is divided, and by extrapolation we can define the other temperatures. And as you can see here, ice point, a mixture of ice and water. This is in equilibrium with air saturated with vapor at 1 atmosphere pressure. We call that 0 degrees Celsius, or in English unit, 32 degrees Fahrenheit. And a steam point is a mixture of liquid water and water vapor with no air in equilibrium at 1 atmosphere pressure as 100 degrees Celsius or 212 degrees Fahrenheit. So you can see here it is just 2 points we select according to, which is easy to measure and to be reproduced. And Celsius scale is a unit. Actually, in SI unit, we can use that. However, the unit in SI is Kelvin, but we can also use Celsius. Celsius is, if we divide the temperature scale between 0 degree and 100 degrees Celsius to 100 different spaces, we call each one of the points between these two as 1 degree Celsius. And we have also Fahrenheit scale, which is English unit. Later we will see the relationship between the Fahrenheit and Celsius scale. And we have thermodynamic temperature scale like Kelvin and Rankine cycle, which is more accurate when we are dealing with the temperature in thermodynamics studies. Kelvin scale is for the temperature scale, nearly identical. The Kelvin scale is the ideal gas temperature scale. Later we will see how we can deal with that. You can see here a constant volume gas thermometer would read negative 273.15 degrees Celsius at absolute zero pressure. This is the minimum pressure up to now human beings can reach to that. You can see here pressure is 0, and the lowest pressure we have here, and which we call that absolute vacuum. and volume is constant, then the temperature for that will be negative 273.15 degrees Celsius, which is equal to 0 Kelvin, actually, not degree, 0 Kelvin. And here are some important relationship between Kelvin and degrees Celsius. Later on, you may need to convert temperature from Kelvin to degrees Celsius, or vice versa, and also about the Rankine and Fahrenheit, Rankine and Kelvin, Fahrenheit and Celsius. You can see, you can use these equations to do these conversions. Later we will see some example to do that. So according to this, you can see 0 degrees Celsius is 273.15 Kelvin. And you can see also in for these thermometers, how is it, degrees Celsius, Kelvin, Fahrenheit, and Rankine, how much is it? You can see 0 degrees Celsius, 0 Kelvin is negative 223 Celsius, and vice versa. You can see for other point as well. But notice one important thing for the these temperatures scales, different temperature scales, that temperature difference is same. Delta T in terms of Kelvin, or different temperature difference between two different points or temperatures in Kelvin scale is equal to temperature difference in Celsius scale. So this is important. You can convert like this, Kelvin to degrees Celsius. You need to do that when you are going to just study 1.1 temperature. But when you are going to use temperature difference, no matter if you use Kelvin or Celsius temperature difference, it's okay. It will be equal also for Rankine and Fahrenheit. And this is some definition how was initially. You can see also one important thing here, not important actually, but you can see here the relationship between the units of the different temperature scale. 1 Kelvin is equal to 1 degree Celsius, which equal to 1.8 Rankine, and you can see Rankine and Fahrenheit are equal, and units for Kelvin and Celsius is also equal. So this is temperature difference actually, or the magnitudes of various temperature units. And here is an extra explanation about the reference temperature for the Kelvin. It was initially ice point, which is the temperature at which water freezes or ice melts. Then it is now changed to the reference point, was changed to much more precisely reproducible unit point, which is triple point, the point which water is in all of three stages, three phases of water, like you know about that, liquid, gas, and solid, I mean ice. Then the point, the temperature which we can find these three phases together or simultaneously is 223.60 Kelvin. Just you can see here how much is different. Here is more accurate. And here also some extra explanation about about the revisions of the temperature and temperature scale. You can see here it is out of our scope for today's session, but if you need more explanation about the exact temperature which nowadays is being used as the source and to define or find the temperature scales, you can go to this slide or your textbook. The other important properties is pressure. As you may know, pressure is the normal force exerted by fluid per unit area. Its units is Pascal, which 1 Pascal is 1 Newton per meter squared. You can see here, so pressure depends on the force and also the area which this force is acting. You can see here an example, two different individual or two different people. You can see here, the area in their, their foot is their feet actually, or area of their foot is equal, but the mass of their body is different. So the pressure which exerted to their their foot is also different. Because of that, this guy actually may feel more pressure on his foot, and the pain will come much earlier than the other guy. So this is one reason why you should reduce your weight and stay fit. And the other unit for pressure are bar, which is 10 power 5 Pascal, and also megapascal is 10 power 6 Pascal, or you can see the relationship between the bar and megapascal, and each bar is also 100 kilopascal. This is the relationship between different units of the pressure. And also we have atmosphere. Atmosphere is the pressure which this is useful when you are going to deal with the pressure on Earth. The scientists have measured the pressure of the atmosphere, which is the come from the weight of the air around the Earth's surface. They call that 1 atmosphere, which is equal to 101,325 Pascal, or simply 101 point something kilopascal. So this is atmosphere. You can see relationship between the atmosphere and Pascal. It is useful when you are going to dealing with to measure the absolute pressure. Later we will see what is absolute pressure. And here are the other units for the pressure: kilogram force per centimeter squared. This is for the other units for the pressure. You can use them as well, or you may see these units in different examples. But according to the measurement or method of measurement of the pressure, we have three different types of pressure. Absolute pressure is the actual pressure at the given position. So this is actual pressure. I mean, here on Earth, if you are going to measure the pressure for a volume, for anything, you should, we cannot get rid from the atmosphere pressure. We have atmosphere pressure on Earth anywhere. How we can measure the actual pressure? We should remove the atmosphere pressure from the measured pressure or the gauge pressure. So the difference between the absolute pressure and the local atmospheric pressure is gauge pressure. Most pressure measuring devices are calibrated to read zero in the atmosphere, and so they indicate gauge pressure. So when you are using a gauge to measure the pressure, usually, it doesn't need to remove the atmosphere pressure from that, because it is already, considered. So gauge pressure usually is measured only by that equipment. And vacuum pressure is the pressure below atmospheric pressure. Okay, so let's see in this diagram about that. This is P atmosphere. We have this pressure everywhere on Earth, like this. But sometimes, for example, in a tire, we use some kind of pressure, air pressure. We increase the pressure to increase its pressure to increase its volume, actually. So the pressure is higher. So then when we use a gauge to measure the pressure, it will give us gauge pressure, or the pressure difference between the inside the uh, tire and the atmosphere. This is gauge pressure. But actually the absolute pressure for tires is this much at P atmosphere pressure plus gauge pressure. What about vacuum? It is the time when we reduce the pressure. Imagine we bring out the air from something, we reduce the pressure from that. You can see here P atmosphere is constant like before, 100 something in sea level. And you can see here again the absolute pressure is lower than P atmosphere, so we have some kind of vacuum. This much is the vacuum. And absolute vacuum is when we don't have any, the P vacuum is equal to P atmosphere. Zero absolute pressure. We call that absolute vacuum. So in this text, in this book, and in this course, actually, the pressure P will denote absolute pressure unless specified otherwise. So from now on, anytime we say the pressure, we mean absolute pressure, this one or this one. In other words, includes the atmosphere pressure, not the gauge pressure. And the other interesting things about the pressure is the variation of pressure with depth. Imagine this is the water, as you know, by the pressure of fluid at rest increase with depth as a result of the added weight. You can see here, because as long as we go deeper, the weight above or acting on that point is higher, then pressure it will be higher as well. You can see here. So delta P, difference temperature, for example, P1 and P2 in different depths will be depends on the the depths. And because, as I said, we have atmosphere pressure on Earth everywhere, so the pressure for in a specific depth, H of the fluid of a liquid will be summation of P atmosphere, which comes from the atmosphere, and rho GH, which come from the weight of the fluid at that depth. So P, or absolute pressure, is equal to P atmosphere plus rho GH, or P gauge is rho GH. And you can see how we can calculate delta P for that depth. You can see here. But this is, that I said it is about the high depth, higher depth. But in a room filled with a gas, the variation of pressure with heat is negligible. So usually in a room where we just have a gas like air, we can, you can see here P top and pressure at the top near the ceiling, and at the bottom, this is a 5 meter high room. You can see the pressure difference is negligible. It is in terms of the thousands. So we can ignore about this pressure difference in a room. And when you can see here it is 5 meters. But in liquids, pressure in a liquid at rest increases nearly linearly with distance from the free surface. You can see here. So easily we can use this equation to find the pressure at depth of H. It is H. So at the surface we have P1. At the surface is P atmosphere, because we have only the air or atmosphere acting on that. At the depth of H, the temperature, the pressure is increased because of the weight of the fluid as uh, this much, rho gh. And this is also interesting that the pressure for a liquid at each depth is only dependent on the its depth. That's not related to the shape of it. You can see here because all of these points are in same depth, so pressure at those points is identical. And from these definitions, for pressure, we can reach the Pascal's law. The pressure applied to a confined fluid increases the pressure throughout by the same amount. In other words, when we use this F1, it causes P1, it is equal to P1 and A1. P is the pressure on this surface, A1 is the surface area of this system. Then, the pressure throughout the system will be same, so that it will reach to this surface, and it will be equal to F2 plus P2 H2. Because P1 and P2 are identical or same according to the previous slide I showed to you, in same, you can see in same height or depth, then F1 divided by A1 will be equal to F2 divided by A2. By manipulation, we can reach this equation. F2 divided by F1 is equal to A2 divided by A1. You can use this equation to use a small force to to push something and to produce higher force just by changing the area which the fluid pressure is acting on. That small area here, big area here. Small force is required here to move this one to produce more force here. So the area ratio A2 to A1 is called the ideal mechanical advantage of the hydraulic lift. You can find this, we are using this definition for the hydraulic lift in the many workshops nowadays, which we use small force to lift large weights. And one equipment which being used to measure the pressure or pressure difference actually is the manometer. You may know about that. Imagine we have a tube like this, fluid is flowing through that. As you may know, the pressure here, from here we are interested to know how much is the pressure difference between these two. We can add this manometer, which is U-shaped equipment. You can see here, because of the pressure difference between these two, the liquid, which can be mercury or alcohol or oil, stays in different elevation, and you can see here the difference is H. So by measuring the pressure drop across a flow section or a flow device by differential manometers like this, when then we can find the pressure difference between P1 and P2, or 0.1 and 2, like is rho 2 minus rho 1 times G H. This is H. G, you know about that, and rho 1 is the density of this fluid, and rho 2 is density of this fluid, which can be mercury, alcohol, or oil. We can use a manometer to measure pressure inside the tank or something. Again, with same calculation, you can see here pressure here will be acting on this place, pressure, atmosphere pressure acting on this place. So this H is due to the pressure difference inside the tank and the atmosphere. So P at point 2 will be equal to P atmosphere plus rho G H. So by this we can find the P2. But when we have different fluids inside the tank, then we can also consider the pressure at the bottom of that, the barrel, for example, here depends on the density of different fluids. Then we can find the P1 at the bottom of that in terms of the, we have P atmosphere on top of that, and we have the pressure increment due to the weight of different fluids, and also because they have different density, then this rho gh will be different for them. Finally, by this general equation, we can find this pressure at the bottom of that barrel. And other pressure measurement devices are Bourdon tube, which is a tube when the pressure is acting, its shape is changing or its travel distance. Pressure transducers, they have them, which, the pressure changes will cause a mechanical movement. Then that mechanical movement can be seen as the voltage or resistance or capacitance changes as well. Then we can measure the pressure. We have a strain gauge, which is worked by having a diaphragm deflect between two chambers. And again, by this, we can measure the pressure. And also we have piezoelectric transducer, or we can call them, or simply call them as solid state pressure transducers, work on the principle that electric potential is generated in crystalline substances when it is subjected to mechanical pressure. So you can see here some different methods to measure the pressure. Why it is important? Because pressure is important in thermodynamics area, so it is better to know how we measure that pressure to study. And the other, actually, I told you about the pressure or atmosphere pressure. How that pressure is measured by this barometer. Atmospheric pressure is measured by this device. We call that barometer. And what it is measured is barometric pressure. So as you can see here, which is defined as the pressure produced by a column of mercury, which with 760 millimeter at 8 in height. This is when this is 760 millimeter at 0 degrees Celsius, and where the gravitational acceleration is this much, 9.8 something. We call that standard atmosphere. This is the method. You can see here, open pan something, and here we have a cylinder, and you can see, because of the pressure and this surface, the mercury will go through this tube. It goes up. When it reached the 760 millimeter, we call that standard pressure, and it is independent from the diameter of the tube. You can see here for different tubes, this height or this height is same. You can see, why it is important, because in higher, why we measure this at sea level, actually, this 760 millimeter, but in higher elevations it will be lower. So the pressure of the air is lower. So at high altitudes, a car engine generates less power and a person gets less oxygen because of the lower density of the air. Pressure is decreased, then density of the air is also decreased. Okay, now I have introduced you some basics, some units which you require for your calculation to solve different problems related to the thermodynamics. Now I'm going to tell you how to solve problems, which we call that problem solving technique. Step one is to problem statement. You should be able to state a problem, to say what is a noun, what is unknown, what we are going to find. Step two is to draw a schematic. It is very important. When you draw a schematic of the problem, you can understand if you are in the right path to solve the problem or not, and the problem will be more clear for you. Step three, you should write the assumption and approximation. As I said in previous slide, for example, you can say a steady flow as one of your assumptions. So you should write assumption and approximation. And step four is physical laws. You should write that, for example, you should know about the gravity, how much is it? And step five, the properties. As I said, in thermodynamics, we are going to deal with matter and energy. So you should know the properties of that matter. For example, the ideal gas like air or water, which is dependent on the temperature. We have different tables for them. You can find these properties in tables. And step six is calculation. If you have done this, if you do these steps correctly, the calculation will be much easy for you. You should just notice about the units, about the accuracy. We will see. I will tell you something about the accuracy of the results. And step seven is reasoning, verification, and discussion. You should check your answers if they are reasonable or not. You will see some example what I mean from the reasonable answers. Why we are going to go through these steps? Because we are going to solve the problems in easy way. You can see here is the problem. We have hard way, we have easy way. We are going to solve the problem in easy way. We are going to find the easiest way to solve the problem. For example, here is the assumption. You can see here we have a problem given is air temperature in Denver. We are going to find density of the air. We have the temperature, we are going to find density of the air. What is missing? Missing information is atmospheric pressure. So we can do this assumption. Take this assumption number one, take P equal to 1 atmosphere. It's inappropriate. Why? Because it ignores effect of altitude will cause more than 15% error. When you understand this error, later on when you calculate. What about then? Okay, let's again consider if we can have another assumption. Assumption number two, take P equal to 0.83 atmosphere. It is appropriate assumption. Why? Because it is ignores only minor effects such as weather. So for example, in this example, when we have air temperature in some places, then we are going to find the density of the air. We can't ignore the atmospheric pressure. We should know that and consider that, but we can forget about the environmental condition like wind or something in that day. So it may not that much affecting in the final value for density of the air in that area. And you shouldn't forget using of different equipment like computer, like your calculator will only help you to find your answer easier. It will not help you to find the answer. It will not give you the answer. It just help you to find the answer easier. The answer is depends on your reasoning, your knowledge about the problem. Here is another example how you can check your answer. For example, energy used for a house is $100 per year. After some manipulation, for example, using insulation material for the house, energy, then you can calculate the energy used for that house. Finally, you reach this line. Energy saved by insulation is $200 per year for that house. Is it possible? No, it is not possible. No, energy use is given, it is $80 per year. How you can save $200 per year? It should be a fraction of these $80. So by this you can check your final answer if it is correct or not. And always do not forget to write your answer or solve the problem organizedly. You should write the answers step by step and clearly. And this is also important, a remark on significant digits. Your final answer cannot be more accurate than what you have. For example, volume and density is given 3.75, 0.845 kilogram per liter is given. As you can see here, we have three significant digits. Here we have three significant digits. And then we are going to calculate the mass. As you may know, mass is equal to density times the volume. We have volume of that substance. We have them. Then we can find the mass. But you can see here, if we do this multiplication in our calculators, we will reach this. But the final answer cannot be this because the accuracy of the values which we have here is three significant digits. So the final answer should be written like this. Should be rounded to three significant digits, 3.17 kilogram. So we should round this to three significant digits. Why this is important? Because later on we may have quizzes, we may have online exams or exams. The final answer should be something like this. If you don't write something like this, you may lose some marks. So try to understand the significant digits importance for your calculations. Okay, let me just briefly tell you what I said today for today's sessions. As a first session for this subject, I told you about thermodynamic and energy. I told you about importance of dimensions and units, system and control volumes. I continue with the properties of the system. I told you about density, state, and equilibrium. We reviewed the process and cycles. We reviewed some basic concepts about temperature, pressure, and also the manometers. And we discussed about the barometers. And finally, we reached the problem-solving techniques. So by this, we reached the end of the first session. I hope you enjoy watching these videos for your first session. Next session we will go for the chapter 2, which is about the energy and properties of the substance.